want to talk about definite integrals and start with a really concrete example and then talk about some generalities about definite integrals. So here's the kind of problem that, let's say, estimate the integral from 1 to 4 of the square root of 3 plus x squared dx using the midpoint rule with n equals 6. Let me get the better chalk, thicker chalk. Okay. This will show up better. See if I can do this right. Okay, so how do we set that up? We need A and B. So remember, this notation means take the function from 1 to 4, root 3 plus x squared, whatever that looks like. I'm not going to worry about too much what it looks like. And find the area under that curve. I'm going to say, it's not quite that every time, but I'm going to say in a little bit later in the video what might be different about that. Okay? But that's the idea, is to approximate this area. And we're going to split that up into a bunch of subintervals, take the midpoint of each subinterval, and use a rectangle based on those midpoints. So A here is 1, B is 4, N is 6. Delta x is, you're chopping up the interval of length 3, b minus a, into n pieces. In this case, that's 3 over 6 is 1/2. So, to have a little bit more accurate picture, but only of the interval. You really need an accurate picture, really only of the interval to do the bookkeeping. We're slicing it up into 6 pieces, and the endpoints of the intervals are going to be 1, 1.5, 2, 2.5, 3, 3.5, 4. But the thing about the midpoint rule is we actually subdivide a little further. We're going to be creating a rectangle on this subinterval, but we're going to use the midpoint of it to sync up with the graph of the function. And so that's going to be things like 1.25 or 1.75 or 5/4 and 7/4 to use fractions, which is prettier. Okay, so how does that work if we try to systematize it? Our xk bar, that's the midpoint. That's a nice notation that suggests the midpoint of the kth subinterval. We're going to start from A, and then we're going to add in a delta x over 2 to get into that first midpoint. And then we're going to keep adding delta x's. And how many delta x's are we going to add? We're going to add k of them. Oh, except wait a minute. The trouble is we usually start k equals 1. I like to start at k equals 0, but the book usually starts with k equals 1. So that would be, you get into the middle of the subinterval, but then you jump out of it and you actually already go to here. We don't want to do that. So, in fact, what we can do is, if we're going to start with k equals 1, we can add a delta x, but then go back. And so, in fact, minus would be good. Oops. And so, the summary is it's 2k minus 1 all over 2 delta x, when you put it over a common denominator. That's the magic formula for the midpoint rule points. Okay, so, unfortunately I have to erase. You can always rewind the video if you're missing something. Okay, so our area, or integral, is approximately going to be sum of height times width. That's always the idea of the rectangle, any kind of rectangle method. Okay, and that's going to be sum k equals 1 to 6 of delta x, which we've got, times f of all these midpoints. So I'm going to write out a pretty general formula, and then really write it out absolutely in gory detail. And then I'm actually going to skip the whole step where you plug everything into the calculator, because that's kind of easy and boring. So delta x is going to be 1/2, and then f of xk bar that's going to be, take that function, the square root of 3 plus something squared, and you're going to put in the xk bars in there. Well, let's see. Let's make this explicit. A was 1, and then delta x was a half, and so we're getting 2k minus 1 over 4. Oh, let's actually check that. 2k minus 1, the special thing about that is they're always odd numbers. And so I'm going to get odd multiples of a fourth. Well, that makes sense. 1 plus 1/4, 1 plus 3/4. The next one would be 2.25, which is 1 plus 5/4, or 9/4. Okay? And in fact, if I put it all over a common denominator, it's just 2k plus 3 over 4. A bunch of odd numbers starting with 5, when I put in k equals 1, over 4. So that simplified form can be put in here. Okay, so that's what you end up having to calculate for this approximation. And so that's going to be a half times the square root of 3 plus 5/4 squared plus the square root of 3 plus 7/4 squared plus the square root of 3 plus 9/4 squared plus the square root of 3 plus 11/4 squared plus the square root of 3 plus 13/4 squared plus the square root of 3 plus 15/4 squared. Now, we can check that. That's not supposed to exactly be the end of the interval, but it should be pretty close. And remember, the end of the interval was 4. It was 1 through 4 that we're integrating. And that's almost 4. It's just that quarter away, 1/2 of a delta x away. And then close the parentheses. And that's what you'd actually have to plug into the calculator to get this approximation. Now, you could do it in that kind of explicit detail, and that's a lot of button pushing. Or you could try to do this guy. If you have the new operating system on the TI, it's a little prettier, but here I'm going to show it with the old version. You could do sum of a sequence where this is the formula for the sequence, 1/2 times the square root of 3 plus, parentheses, 2k plus 3 over 4 squared, close for the square root, and then k 1, 6. The sum of a sequence of numbers based on the variable k, where k goes from 1 to 6, and where that sequence of numbers is gotten by this formula in terms of k, and then sum it all up, and that's the formula you get for that guy. It's a little bit of a, it's still a lot of keystrokes, but it's a little less than this guy. And the big advantage here is then you could do second entry and just change a few of these things and change the 6 to a bigger number. You'd have to change this and this as well to get a better estimate, more rectangles, but it wouldn't be as hard to change the formula as it would be to enter like 12 or 20 or 100 of these guys. Okay, so that's an explicit example where we had a formula and we didn't really think that hard about what the graph of the function looked like. But let me go back to one thing about that function that was important. Changing gears a little bit. It was f of x is the square root of 3 plus x squared. And that function is always, actually it's always positive. I'm going to say non-negative. It's really always greater than or equal to the square root of 3. So it's always positive. Looks something like this. It's getting bigger as you go up. Something like that on this interval. And so what were we doing when we were doing that summation of the sum? Let me write the general formula again. These widths are all positive. And these numbers were all positive. So I got a sum of a bunch of positive numbers, so I'm definitely getting a positive answer. Well, that makes sense, of course, since we're trying to find the area of this guy. But what if I actually had a new function f? So go away from this idea of f, and let's think about what would happen if I did exactly that same formula, but with a function that had some plus parts, positive, and some negative. Well, what I'm going to get is, if I separate it out into these rectangles, I'm going to get positive numbers from height times width here, but if I don't put an absolute value or something here, which we hate anyway, we wouldn't want to do that. I mean, we'll do it sometimes, but it shouldn't be our instinct. If we don't put some sort of absolute value here, we're going to get positive width times a negative value for f, and we're going to get a negative contribution here and a positive contribution here. The question is, should we do that? Is that a good idea? And surprisingly enough, this is absolutely a great idea. Most of the time, it's what we really want. And in particular, this idea, which is one way to refer to it, is the net signed area. Net meaning that the positive and the negative might cancel out, and you might get a smaller answer than you expected. Signed, of course, means that you're paying attention to the signs, plus and minus. This guy is what links to antiderivatives. If you don't do this kind of style, you will lose the fundamental theorem of calculus, the link to antiderivatives, and that's a huge thing to lose. So sometimes people do just look at the area in the geometric sense, plus and plus, but most often you're going to be doing the net signed area. Two huge advantages. One is you don't have to modify this kind of formula. The sum of the sequence, the summation, sum of height times width, as long as you just let these be whatever values they are, it's going to calculate this guy. That's great. The other big advantage is that a lot of times you can skip this, short-circuit this process completely and use the fundamental theorem. You wouldn't be able to do that if that's a plus. So, in fact, when you write this notation, like the integral from 1 to 4 of f of x dx, that is defined to be the net signed area. If the function happened to be positive, it wouldn't have mattered. That's why it didn't matter yet. Okay? And remember the terminology for this is it's called a definite integral. And that, by definition, really is the net signed area. Okay? So I think I'll separate it out into a different video some properties for this that we'd like to know.